When we're solving a system of linear equations and we're asked to find a solution to a set of linear equations, there are several different methods we can use. The method of substitution is one algebraic method that we can use, which basically we just do a bunch of number crunching and we'll end up with an actual coordinate, the coordinates of an actual point where the two lines cross and intersect. Or possibly we might find out that there is no solution because the lines are parallel and they never intersect. Or we might find out that the equations we're being given are the exact same, and so therefore there are an infinitely number of solutions because they're really the same line. So it's every point on the line that's a solution. But using the method of substitution, I'm going to model that with this set, with this system right here. I like to do this with colors when I'm working on the whiteboard in class. If we look at this equation, it's telling us that y equals all of this. I'll do this in different colors so we can see what's going on. But in this equation, in the same system here, we're also told that y equals 2x minus 1. I'll do that one in black. So if we know that y equals this and y equals that, then why can't we say that these two equal each other? So simply writing them out as x plus 1 equals 2x minus 1 gives us an equation that we now can balance out and solve for x with, because there's only one variable. If we move all the numbers around and in all the balanced ways that we know how to solve for x, we can find out what x is, and then we can plug the number in for x back into one of these equations to find out what y is. But another way to think about it is basically if y equals this up here, which is x plus 1, why couldn't I say then that I'm going to substitute x plus 1 in for this y in this equation? And when I do, I'll write x plus 1 equals 2x minus 1. Or if I want to, it doesn't matter, I can do it the other way around. I can say if y equals 2x minus 1, then why don't I take what y equals in this equation and plug it in to that y in that equation? If I did, I would simply get the exact same thing, but just written in reverse. Instead of 2x minus 1 being on the right side of the equation, it's now on the left side of the equation. Exact same thing. But regardless, what we have here is something that's going to allow us to solve for x. So let's go ahead and take this equation here and let's solve for x. So now I just use my balancing techniques. I'm going to add 1 to both sides. When I do that, I'll have x plus 2 equals 2x. Then I'm going to subtract x from both sides. Remember, whatever I do to one side, I do to the other side. So when I do that, this is going to cancel out. I'll end up with 2 equals 2 minus 1x. There's a 1 there, even though I don't see it. 2 minus 1x gets me 1x, which is the same thing as just x. Now I see that x equals 2. Knowing that x equals 2, I can now put this number in for where x is in either one of these two equations and now solve for y. And that'll give me what y is. So I'm going to do that right now. I'm going to I'll just pick the first equation. It doesn't matter which one I pick, but I'm going to pick the first one. So I'm going to go y equals, now instead of saying x for x plus 1, I'm now going to say, I know that x is 2, so I'll put a 2 in there for x. So now I have y equals 2 plus 1. Well, I know that means y equals 3. So here I found out that x equals 2, and here I found out that y equals 3. Now just to show you that it doesn't really matter which equation I use to plug this x in, I'm going to do it with the other equation now. So let's do it for y equals 2 times, what is x? X is 2 minus 1. If I solve for that, here I get 4, and I end up with y equals 4 minus 1, which is 3. I get the same answer again. That's just to show you that it really does work. All right, so now, if you've been asked for a solution in a system of equations, and you come up with a number for x, a number for y, then your solution is the point where both equations are crossing each other. So the solution needs to be written as a point, like the coordinates of a point. And the coordinates of a point always are x first and then y. So I know x is 2. I'm going to write 2 in there in my parentheses. And then the coordinate for y is 3. And this is what my solution is. A lot of times students either just stop when they find out what x is and they think they're done, or they stop when they find out what y is and they think they're done, and they don't realize that the actual solution needs to be written as the coordinates of a point, because that's what we're trying to find out. What is the point where the two lines are actually crossing? And there's the point. And so we need to write it as a point. Okay, so let's take another example. Slightly harder. Let's do y equals 4x minus 8. This is another set of two linear equations. Y equals 2x plus 10. And again, the thinking is, because this is called the method of substitution, I need to think, do I have information here in this system that's going to allow me to substitute something, some expression in for one of the variables? In this case, I have y equals 4x minus 8. If I want to, I can take the 4x minus 8 and I can substitute it in for this y. Or I can do the reverse. I can take what this says y equals, which is 2x plus 10, and I can substitute it in to that y. Doesn't matter which one I do. Either way, I'm going to end up with this equaling that. So when I'm going to go ahead and take the blue and substitute it into this y. And what I will get is 4x minus 8 equals 2x plus 10. Okay. So now all I have to do is use my balancing methods to solve for x. I'm going to start by adding 8 to both sides, because that will eliminate this 8 on this side when I do that. Oops, getting my colors mixed up. So now I end up with 4x equals 2x plus 18. And now I'm going to subtract my 2x from both sides so I can join my like terms with the x's. That will end up canceling that one out. And I will now end up with 2x equals 18. And lastly, if I divide 2 on both sides, I will end up with x equals 9. So now, sorry about that, that's my notification that text memo is popping in. Probably one of my students needing help. So now I have x equals 9. So here's one part of the coordinate that I need for the point that I know is a solution for these two equations. Now to get to the other part, which is the y coordinate, I need to plug 9 in for x in either one of these equations. It doesn't matter which one. It'll work both ways. I'm going to pick, for the heck of it, I'll pick the second one. So now I'm going to write y equals 2 times 9 instead of x. I'm now writing 9 plus 10. I'm going to continue solving. I'll get 18 plus 10, which means y equals 28. So now that I have my two coordinates for the point, my actual solution for this system of equations is 9, 28. And this is what I would call, this is the point that if I actually graph these two lines on the graph, this is the point where those two lines would cross through each other at that one point. Okay, so I'm going to give one last example of the method of substitution. And this one is just so you can see there's different ways of substituting parts of one equation into another. What if you were given these two equations as your system? Here we see that y equals something. But down here we don't see that one variable equals the rest. What we see is 2x plus 2y on one side. So when I'm substituting in this particular problem, what I'm going to want to do is take this, because this tells me what y equals, and plug it into that equation. And what that would look like is simply, I'm going to take this equation now, 2x plus 2x minus 2 equals 4. And then I can continue solving until I get, I'm going to hurry this up because my 10 minutes are almost up. 4x equals, I'm going to add 4 to both sides, get 8, and then x equals 2. So it's just a slightly different way of seeing the two equations, but can you still substitute one into the other?